Hello geometers and general seekers of truth. Welcome to the lesson on perpendicular bisectors. And let's start with a little bit of terminology. So the word perpendicular, we know from our previous work that it basically means to intersect at a 90-degree angle. So perpendicular, remember, it means to make a 90-degree angle. And the word bisector means that we are going to cut something in half. Thus, when we put the two of them together, we can say that a perpendicular bisector is a segment or line that cuts another line segment in half at a 90-degree angle. Right? It is a line or a line segment that cuts another segment in half at a 90-degree angle. Now let's take a look at a quick example. So say I have two lines like this, and let's say I have a little point here in the middle, and these two segments here are congruent. Let's just call this A, B, and let's call this line here line L. Okay? Then in this example, we can say that L, line L, is the perpendicular bisector of AB. So L cuts AB in half at a 90-degree angle. I forgot to add this, that it has to be at a 90-degree angle. So L is the perpendicular bisector of AB. Now let's look at another example. Let's say that I have a triangle, and we'll call this triangle ABC. Let's see what happens if we were to take the perpendicular bisector of all three of its sides. So I'm sketching here to speed things up, but I'm assuming you already know how to figure out what are the perpendicular bisector of these line segments. So I have these things that cut this length and this length in half. Right? So let's call this point here X. Let's call this point over here Y. And let me get another one, a green one. And let's call this point right here Z. Right. Now let's consider, now that we have, let me make some congruent marks as well. So we have perpendicular bisectors. And let's consider what happens when we make these little line segments here. And let's just call this point in the middle here, let's give it a big dot right there, and let's call it D. Well, let's compare triangle AYD and triangle BYD. Okay, so it's pretty straightforward that those two triangles are congruent because you basically have one pair of sides right here. You have the 90-degree angle in the middle, right there, and then you have a reflexive side down the middle here. So we can say quite clearly with a lot of confidence that triangle AYD is congruent to triangle BYD. And our reason here would be nothing really special, side, angle, side. So from that fact, we can say that AD is congruent to BD by CPCTC, corresponding parts of congruent triangles are in fact congruent. Right? Now, let's consider another pair of triangles. Let's consider these two over here. Okay, so let's look at triangle AZD. Okay, and this picture is getting quite messy here. And then the other triangle that's right next to it right here. But really, for the same reason as what we had before, we do in fact have, whoops, got a little bit away from me there. Let's get back there. Okay, so we do in fact have congruent triangles. So AZ and CZ, then we have a 90-degree angle in the middle, then we have a reflexive side. So now we can also say that triangle AZD is in fact congruent to triangle CZD by the same reason as before. I'm sorry, not CPCTC. Got a little ahead of myself there. But the reason again is side angle side. Then we can say, just as we did before, that AD is congruent to CD by corresponding parts of congruent triangles are congruent, CPCTC. Right? Now, that's very convenient because if you look at these two statements right here, what we can say then is that all three of these segments that go from that point D, which we can say that AD and BD and CD are all congruent to each other. Okay? Because AD is equal to BD and AD is also equal to CD, so all three of those segments are congruent to each other. Now the question is, why does this matter? Well, the reason that this truly matters is that it solves the hospital problem that we were working on from a day before. So let me introduce something to you here called the perpendicular bisector theorem. And it says that the perpendicular bisectors of a triangle, of all three sides of a triangle, meet at the same point. Okay, so let's write that down here. So not only do the bisectors, or the perpendicular bisectors of a triangle, intersect at the same point, the intersection is equidistant from the sides. So we look at our example up here. When we took the perpendicular bisectors, that's this green line, this blue line, and this red pinkish line right here. They intersect at the same point, and they're also equidistant from each of the corners, namely point A, point B, point C. And the intersection of that point is known as the circumcenter. And so the circumcenter is the point where the perpendicular bisectors intersect. Where the perpendicular bisectors intersect. All right. So in our example above, D is called the circumcenter. So our example from above, D is the circumcenter. Right. And for those of you who've been following along truly and considering the ramifications of this, this is the solution to the hospital problem that we talked about in class. Right? So if you needed to construct a point that's equidistant from three other points, you want to go about constructing the circumcenter. So I'm going to end this video here and start another one where we look at some of the examples in terms of solving problems. Thank you for watching and have a